Welcome to NPTEL course on power system protection. In this lecture related to distance link, we will have protection of series compensated lines part 2. So, the coverage will be on apparent impedance issues, zero sequence compensating factor and available protection approach. Two approaches we will discuss on it. Last lecture on series compensation in part 1, we discussed on the operation of protection of the capacitor, the corresponding MOV operation, air gap flashing and the breaker operation. Then we discuss on the directional link issues, current inversion, voltage inversion and how the solutions to directional link can be achieved. In this lecture, we will focus on the distance relay issues and the solutions. Come to a system, simple system as we have discussed earlier also. M n is a transmission line section and we have a capacitor at M end and we have a relay at R, a distance relay which takes the corresponding voltage and current at bus for the line M n. Now, we know as we have discussed earlier also that the capacitor has its own protection, metal oxide varistor. So, whenever the current becomes more through the capacitor, voltage across the capacitor goes high, capacitor has a specific rating of voltage. If it goes beyond that, it is dangerous, may damage the capacitor. So, MOV operates and then the functioning of spark gap and the bypass breaker that we have discussed in the last lecture. Now, when it comes to the situations as observed by the distance relay here, then what are the associated issues? In the whenever a fault happens to be there in the line, fault current flows through the capacitor, through the relay also, they are in series. Now, that whenever the capacitor happens to be there, so in the fault loop capacitor may be there or capacitor may be bypassed by the MOV and the spark gap arrangement. So, when capacitor is there in the fault loop, one reactance, one impedance seen by the relay. When the capacitor is not there in the fault loop due to the bypassing provision by the MOV and the air gap, then in that case the fault loop does not have the capacitor and it will behave just like the normal transmission line. So, with that situations, how the corresponding relays is, we will have some discussion and then we will go to the further details. The impedance of the protector line is modified by the series capacitor, true, varies depending on the state of the air gap and or MOV operation. Note, the corresponding series capacitor, state of the series capacitor in the fault loop depends upon the MOV and the spark gap arrangement. The apparent impedance even moves to fourth quadrant in the RX plane, we have observed in the current and voltage inversions. So, that leads to such a situation. Relay problem is more prominent for low fault currents. So, what we see that when the fault current is low because of the fault may be very far away or in case of the source impedance is very large or the corresponding fault resistance is very large, then in case of that the fault current becomes low and in that case the corresponding voltage across the capacitor will not be higher than its rating and MOV operation and spark gap operation will not be there. It means, in the fault loop the capacitor will be there. So, that you can say that is a critical issue, you can say that, and furthermore sometimes that the corresponding MOV may be operating for a longer period of time before the spark gap bypass and so. In that situations, that the low current you can say situations, then you can say that we have the apparent impedance is seen by the relay will be more problematic case. Normal distance relay functions cannot offer reliable protections for the low current faults. They may fail to pick up internal faults even when significantly overreaching is provided. furthermore, we have already discussed in earlier lecture that because of this LC in series, subharmonic frequency component is there in the signals, and that you can say that leads to oscillations, and therefore, the phasor estimations accuracy, and that leads to the corresponding effect. That effect is also observed in the apparent impedance, and which may lead to reach issue, reach setting perspective. So, we will see consider more details on these issues which we have addressed here in the perspective of distance relay in the presence of series capacitor. Now, let us have these simple issues, and then we will go to the more details one. Now, we know that series capacitor, presence of series capacitor in the fault loop changes the capacitance, changes the equivalent reactance, the impedance as seen by the relay because of this capacitive reactance, which is having minus of j x c as compared to j of x l of the line. Now, one perspective is that a straightforward solution comes into our mind. No, if you measure the corresponding current, voltage, current will be series. So, current will be same here or here. If you measure the voltage in the line side, you understand here line side means position at here, not at here. So, if you measure the corresponding measurements by the relay, the voltage measurements become to the line side beyond the capacitor, and the corresponding relay sees this as the forward zone. Then this path does not encounter the capacitor from this to this. So, no voltage inversion, no current inversion will be observed by the relay for the forward fault. That means that the corresponding for the system, the corresponding in current inversion etcetera may be there, but at this point the corresponding current or voltage inversion will not be observed, and that solves the purpose. But note that if you have this corresponding relay at this one, faults for this side or fault within the line also at F will be not be considered seen by the relay if you consider this as a forward thing. If you accommodate this corresponding F in the quadrilateral or more relay setting by offset arrangement and so, then this you consider will see the issue of current inversion, voltage inversion in the system. This will be a reverse direction fault that has to be accommodated in the characteristic, which is not that easy also. So, this is about line side measurements. In the line side measurement, as we have discussed, this is the M point here, and then this is the normal line we are observing without capacitor. Now, you can say that with capacitor what happens, you can say that if you consider the line side, the relay still see the same line impedance from this to this. So, absolutely the without capacitor, with capacitor, the impedance seen by the relay in the forward direction will be same. So, the absolutely the problem is solved for this part, but for the reverse part there is problem. Now, if you go to the bus side measurements, which you usually do, which we have discussed till now in general. So, the relay will be positioned at here, and the corresponding measurements are you can say that the voltage measurements is the bus voltage, and the corresponding current you can say to the line. In that case, what we will see that in the forward direction of the relay, the corresponding capacitor comes into picture. So, in the fault loop the corresponding capacitance will be there, and then if the capacitor is in the fault loop, the equivalent impedance or the reactance becomes less minus of j x c, and if the in the fault loop the capacitor is bypassed, then there is no capacitance. It means that it is normal line impedance up to the fault point. So, if you have you can say that this is the dotted line is for the without the capacitor. With the presence of capacitor in the fault loop, the corresponding at this point the capacitor is at the relay location sending end side from the M bus. So, the corresponding depending on the capacitance compensation minus of j x c, this dip will be there in this R x plane, and then you can say that it will be again increasing for this line section this to this with the corresponding R and x value of the line in parallel with this. So, therefore, what you say that this dip you can say that this will be same till the setting of the zone 1 settings of the arrangement or the other settings. So, this for the zone 1 setting we have shown. So, what we see here you can say that the fault at F 1 just after the capacitor will be this point, and then the end you can say that will be this point, and accordingly you can say that we have a zone 1 setting for this you can say that without the capacitor becomes like this that we have shown. So, what we say here you can say that is that if we consider the line side measurements at this point, if we consider the burst side measurements at this point, then in the burst side measurements the capacitive effective is coming to picture in the apparent impedance, but here in the line side measurement the capacitive is not coming into picture, but this has associated issue that it is not able to take care of this portion of the consider this essence the between the bus and the corresponding capacitor connection and so. And if you see the reverse side, then the corresponding capacitor is being encountered. If you see, you can say that here in the forward side capacitor you can say there, in the reverse side no capacitor is there. So, in conclusion, if you say that both options of line side or bus side has certain advantage and certain issues or problem associated. The series capacitors are still there either in the forward or in the reverse direction, whatever options we select. Now, suppose the capacitor is the midpoint, then we have you can say that bus M and bus N, and then we have relays at both the end, interconnected system, distance relay. We are considering R M let us first, and similarly we can see also from this R N side because of the symmetry. Now, with MOB operation, large fault current, suppose a fault happens to be here, large fault current happens to be there, MOB operates and the corresponding capacitor is bypassed. So, simple this line. So, this is zone 1 setting. So, this is the Morley characteristics. Now, without MOB operation, MOB does not operate, then capacitor will be there in the fault loop. So, this is 50%, then the corresponding capacitance value deep value, and then again you can say that the corresponding line section, let us say next 30% or so, that you can say that is N. So, this 30% becomes this. So, therefore, you can say that the corresponding characteristic what you have copied from here for the zone 1, and then you can say that the corresponding happens to be this characteristic. So, what we say here that in this case the there may be overreach phenomena, and so with the presence of capacitor and not capacitor. So, in this kind of environment we can have a reduction in the zone 1 setting, that is one approach. The other approach you can say that however, the corresponding compensation becomes very large, that becomes difficult, and then in case of the capacitor is let us say 70%, then 50% plus 70 is minus 30%, again this 30% that becomes 0 kind of thing. So, that situations becomes pretty difficult to consider to adjust the zone 1 setting when capacitor is in the circuit during fault. So, the other problem you see here from this side and that side, if the zone 1 of you can say that R M and R N are reduced to below 50%, that is why I am talking about. If the corresponding zone 1 becomes less because of the series compensation, X L minus X C, so that becomes much smaller, then if the zone 1 setting from this side becomes less than 50% and from this side also less than 50%, the overlapping patch in the network becomes 0, there is no overlapping. That is a not acceptable in the protection schemes, because that portion will be left out from the zone 1 setting from the primary protection. So, that will be taken care in the zone 2, because that is extended one. So, in that case overreaching one, that case the zone 2 will be operating at a later time, which is also not desirable. Now, both end compensation is also an application area. So, let us say you can say that this relay which is line side measurements, because it does not encounter the first capacitor, it can avoid, but see you can say that it will see in the forward direction the second capacitor in zone 2, because this is also in line end. Now, what happens that if you see the corresponding in the Rx plane the corresponding impedance, then what you say that at this point for this there is a dip, the corresponding C1 value, then the line impedance, whole line impedance increase like this, and then again you can say that a dip for the C2 portion, and then you can say that increase for beyond you can say that that you can say that N and so. Now, what will happen here? So, here you can say that if you see the corresponding point here, the zone 1 is set to be let us say 80% for line side measurements, zone 1 will not have any problem, but you can say that if you see you can say that F1 which is just after the capacitor C2, then if you see this F1 and F2, then both you can say that point now F1 you can say that just after the capacitor and F2 just few kilometers from bus N, then you can say that if you see this you can say that this becomes F2. So, this F2 becomes the point you can say that the both F1 and F2 will be shown in zone 1 of the you can say that from the setting at Rm. So, that becomes a problem because of this you can say that the role played by this capacitor C2 in the fault lobe. So, that however, these two you can say that fall in the zone 2 perspective, and if F2 will be seen in zone 1, then this relay may trip before the zone 1 of you can say that bus N. So, that is also not acceptable in protection arrangements. Now, we will consider how the corresponding apparent impedance calculation will be in the presence of series compensator line. So, we have considered a simple series compensator line, MN line, series capacitor at bus M side, and we are looking at the relay R at bus M. So, which is at the bus side connection, both voltage and currents. Consider a fault which is having a x per unit distance from bus M, and then we will analyze you can say that apparent impedance the way we analyze in all the analysis before for the distance relay perspective. This is a line to ground fault case. So, let us you can say that see here VAM equals to VAM plus VAM equals to VA1, VA2 and VA0 at M bus. But then again you can say that using the fault point voltage. So, VA1 F plus VA2 F plus VA0 F and the other you can say that portion from the sequence diagram perspective, we say for VA1 M, VA1 F plus I1 M x Z1L minus JXC, x Z1L minus JXC from the positive sequence diagram. From the negative sequence diagram VA2 F plus I2 M x Z2L minus JXC, x Z2L minus JXC up to the fault point, and then VA0 F I0 M x Z0L minus JXC. So, in all the three terms we find out JXC, because in all the sequence diagram XC component will be there in the circuit. So, when you can say that we have the algebraic manipulations, we got the concept that the VA1 F plus VA2 F of and VA0 F they become combinedly become 0, and that you know, because at fault point the VF will be phase A to ground fault case. So, that will be 0. Now, we can say that similar to what we did in the line to ground fault phase to ground fault case for phase A to ground fault, it will be done like this. What we did here you can say that this is positive sequence, this is negative sequence and then the 0 sequence. For positive sequence and negative sequence for the line they become same, and then we analyze, and then the 0 sequence part we have segregated. We will add and subtract you can say that the corresponding components of I naught m x of Z1L minus of JXC to get the corresponding combination like this. So, x of Z1L minus JXC IAM, IAM is IA1 m plus IA2 m plus I naught m, IM plus that K naught I naught, K0 I0, that 0 sequence compensating factor and the corresponding 0 sequence current. So, that you can say that relations you can say that we are keeping here also similar to that, but keeping that you can say that we say that the Z apparent for the series compensator line in this configuration, that becomes equals to x Z1L minus JXC, that equals to VAM upon this factor, this is the current. So, this denominator you can say that we see this IM plus K naught SC IA0 m. However, the K0 SC becomes you can say that from this relation if you see that becomes equals to the 0 sequence impedance in the path, this part minus the positive sequence impedance in the path, this path upon the positive sequence impedance in the path. So, this becomes equals to if you see here the JXC cancels out. So, this becomes x Z0L minus x Z1L upon x Z0L minus J of XC. Now, we see here in this K naught we have earlier Z0 minus Z1 upon Z1. Now, we have this relation, and in this relation if you see here we have J of XC and also x. X is the location of the fault. So, therefore, we conclude that the 0 sequence compensating factor is a function of distance. Note that is a big challenge, because the distance relay does not know the distance of the fault. It has a setting from the 0 distance to the reach 0.8% or 0.9%, 0.8 pu or 0.9 pu depending upon the corresponding zone 1 setting. So, it does not know the corresponding distance. So, this cannot, you can say that cannot SC for the series compensation is will be unable to calculate, and the cannot, you can say that SC is a function of, you can say that this and J of and the GXC part. That means that you can say that this is no more, you can say that for the normal transmission line, and the GXC plays a role in this one. So, also the distance. So, being a function of the distance of the functions, this cannot be exactly found out. So, what is being done in many, you can say that literature will find that they take a fixed value for this cannot SC, and using the corresponding the error part into the uncertainties in the measurement in the system, and accordingly that is being adjusted in that part. Now, in detailing more on this operational perspective of the corresponding protection arrangement in the capacitor, the MOB puts lot of challenge to the protection of the transmission system. See here, whenever the corresponding current becomes very large, the MOB being a nonlinear function, it starts conducting because voltage across it becomes larger, and a part of, you can say that MOB, the current will be there in the MOB. Now, the corresponding voltage becomes, the current becomes larger, means the MOB CR current becomes more and more. So, therefore, the corresponding equivalent of this part during the transient process, during the fault in the system, this becomes equals to this, where this the MOB offers a resistive part. So, this is an RC combination. So, therefore, you can say that the corresponding equivalent impedance will be now R and X, where N X R both are a function of, you can say, the corresponding current in the systems. Note that if the I is small, this I mob through the MOB is 0, only the C function. So, there is no, you can say that R in that part. So, that means that you can say that the corresponding impedance offered by this arrangement when MOB is an operational is something is a function of current. Let us see in the RX plane that perspective. Mn, this portion is the impedance of the line impedance in the RX plane. Now, suppose we have, you can say that an impedance Z actual for the fault point somewhere in the line, in this line, fault is associated with an RF. So, RF normal line you have an RF. In a capacitive, in the capacitive aspect, the series compensation aspect, if the current is very high, it means that the capacitor is bypassed. So, it is behave like normal line. So, the RF will be just the we added, you can say that in the normal line case almost horizontal to this R axis. Now, in case the current is low, very low, then the MOB will not operate. So, in the fault path only capacitor will be there. So, there will be a capacitive minus of GXC in this. So, this is low current. So, low current situation will be minus GXC, even this RF is there. So, RF and this part will be there. So, equivalently you can say that the corresponding from this actual impedance of this line up to this point, we have, you can say that the corresponding delta Z which is being changed is in terms of the capacitive effect up to this point. Now, currents can be intermediate between the high and the low. So, they can be intermediate point. So, therefore, you can say that the corresponding impedance seen will be also in these intermediate points between this point and this point. With that, we have solutions now for the series compensational line for the distance relay perspective. Two solutions we will discuss. First one is based on adaptive distance relay, distance series using the current can say that control perspective is current control based approach based on the current of the fault current as seen by the relay, and there is another approach on based on the voltage ratio perspective. So, in the first solutions what is being done, that we in the earlier slide we noticed that the impedance as seen by the relay is a function of fault current. So, therefore, we like to consider that because we know large current means capacitor is bypassed, small current means it means that the capacitor is in the circuit, and intermediate means there will be a MOB and capacitor combination. So, what we say that large current MOB operation, capacitor bypassed, normal line impedance the relay will see. So, at that time the settings will be just like normal line. For low current, no MOB operation, capacitor in the fault loop, impedance decreases. substantially considering the minus of j x c. But intermediate, the effective reach is a function of the magnitude of the loop current, that is the fault current, and the reach you can say that of the distance function reduced by the z effective becomes equals to what we like to set is z set, will our setting will be now different, is a function of current I now, z set equals to z set minus V limiting upon I into angle of the z set. So, what is V lim is a function of we can say that x c. So, that you can say that depends on the system perspective and also the particular the x c. The higher the current, the smaller the reduction. If the current becomes higher, the reduction part is smaller, and as we say you can say that if the corresponding current is too large, then you can say that the z effective is z set, no presence of capacitor. However, if the current is smaller, this part becomes dominant. For current below certain value, the resistance element is effectively blocked. Why? Because the corresponding the corresponding z set minus this part becomes too large, and at times the corresponding z effective vanishes. So, therefore, you can say that beyond a certain limit, the corresponding beyond certain you can say that if the current is less than this limit V limit upon z set, then the relay is to be blocked. You cannot allow that you can say that operation of the zone 1. So, therefore, for this you can say that system transmission system and the relay at here, capacitor at here, if you see this perspective. So, we have the larger one, normal one for the ML line 80% let us say, normal line impedance considerations and more relay setting for that one. Now, with consideration of the lower current when minus of j x c is there in the fault loop, and now in between from this point to this point we are changing the setting with using the currents as seen by the relay for that fault. So, this is what we call adaptive. Adaptive means in accordance with the system condition. We will have on the concept of adaptive more elaborations in the later part of the course. Now, here what we say that if the fault current is larger, then we have a no role you can say that played by this x c. So, then you have the normal setting. If the fault current you can say that is smaller, then the x c is full in the circuit fault loop, but if the fault current is in the in between you can say that the higher value and the lower value, then the setting has to be adaptive in accordance with that one, the equation which we have used in the earlier slide. So, that you can say that is the role played here. So, for very small currents the reach vanishes and zone is practically blocked, that we have seen. For larger currents, the cause of the MOBs and the air gaps to conduct some currents, the reach is reduced according to the current magnitude. So, the corresponding reduction you can say that path is this, the reach is being reduced this one. So, this you can say that approach is based on the magnitude of current, larger current the reach is higher, smaller current the reach is lower. Now, let us see an example for a system 400 kV 365 kilometer system, 40% compensation at the local end of the bus M, only one series capacitor, and we created you can say that take fault resistance with RF, small RF, and then we see you can say that what is happened to the zone apparent for the phase A to ground fault case. So, we observe that you can say that this is about zone 1 setting, normal setting line for the line, the blue curve. Fault is created in the zone 2, next line. So, we see here you can say that in this case with small RF, small RF means the corresponding fault current is significant. So, this corresponding capacitor and the corresponding MOB operation changes the apparent impedance. Now, finally, what happens that the corresponding settling point, that the capacitor and MOB bypass the corresponding capacitor and the corresponding fault is beyond the zone 1. This is correct. Agree? So, what we see that with small RF the current becomes high, the MOB starts operations, and then finally, the corresponding air gap also fires, and therefore, you can say the capacitor is bypassed. But in the process we see because of this LC presence, there will be considered the corresponding subharmonic frequency oscillations, and therefore consider the oscillations will be observed considered for some time. Typically this oscillation remains for around 5 cycles or so in systems, and then the corresponding mob and consider that the air gap operation happens to be there, it settles at the bypasses the capacitor, it settles at a particular point. So, here because it is large current, small RF, the relay is able to adjust to consider in terms of that. But note that in between, because of this you consider MOB operation in the capacitors, the adaptive setting can be observed. So, accordingly you can say the dotted line you can say that corresponds to you can say that the at one instant of time, the corresponding you can say that the current value you can say that depending upon the current value, the dotted line you can say that happens to be an adaptive zone 1 setting. Why you can say that we carry out the adaptive zone 1 setting here? That there is a chance that the corresponding spiraling due to the presence of the short circuit, the subharmonic component may enter into the zone 1. See this example, it will be more clear now. With higher RF in the same fault, same arrangement, same system 40% compression. Now, what happens we see here at the same point fault is being created, line to ground fault is created in phase A. Now, I see here the corresponding apparent impedance settles finally after few cycles of the oscillation settles inside zone 1. Now, the reason behind that, now the corresponding capacitor is in the fault loop. So, therefore, you can say that there will be reduced value of this. Now, what it do you can say that here the corresponding adaptive zone 1 you can say that will go for this one. Now, mind it you can say that the corresponding fault is in zone 2. So, not in zone 1, but here you can say that if you do not do the consider the adaptive things, it enters into the zone 1 and creates you can say that problem to consider from the perspective even though the fault is beyond the line. So, however, if you do the adaptive thing, then the corresponding you can say that advantage can be availed, and this adaptive thing is then based on you can say that is the current control approach based on the using the current through the relay as you have discussed in earlier slides. So, this is using the adaptive setting is based on the current through the relay, and if this can be done, then you can avoid the malfunction of the relay in a better way. This is clearly observed from this example on a zone 2 fault for this 400 kV system. We have second approach also as available in the literature. So, this is called voltage ratio based approach. So, for this you can say that we have two voltages, one is the calculated voltage and the other is the measured voltage by the relay. So, system is here like this. If you see you can say that the relay and the capacitor is at the line end, then for this section zone 1 absolutely there is no capacitor. So, it does not have any problem, but if fault happens to be in the just beyond the capacitor, then if the capacitor is in the fault loop during a fault, then the relay this will consider will find j of XL minus j of XC. So, it will having a equivalent impedance will be much smaller, and therefore, you can say that will be having a overreach phenomena. So, fault in the zone 2 actual zone 2 will be also you can say a fall in zone 1, and that may create problem. To have that in this we can say that approach what is being done, that whether the corresponding fault is in the beyond the capacitor or fault is in before the capacitor, if you can know that, then we have you can say that solution accordingly. So, this you can say approach provides that information. So, what is being done that in this case the V calculations will be done. The V calculation you can say that is calculated by the assuming you can say the fault is beyond the capacitor, assume that the fault is beyond the capacitor, no RF or no mutual coupling in the line is considered. So, V calculated is Z1L I plus K naught N naught for the phase to ground fault as usual, minus of JXC into IA. Here in IA you can say that we are not doing the zero sequence compensating because this is not line. So, the zero sequence mutual effect will not come into picture in the XC part. So, as you can say usual, these are all measured value of the current and the perspective, and K naught you can say zero sequence compensation factor, and so V measured you can say that is another the value that you can say is measured by the relay as usual. Now, you will have this ratio V measured upon V calculated, what we have calculated here for that perspective, and along the line we will consider that if you go you consider changing the corresponding distance of the line from fault locations to fault location from the bus M to consider to the bus N, then we will see consider two perspective, the V measured and the corresponding V calculated. So, here you consider if see V calculated becomes you consider that large value from this perspective, because of you consider that the minus of j x c and all these things. So, V calculated from large value to small value it will come till the p and then it will increase at this point, this is the p point. However, you consider that the corresponding measured voltage you consider from this one, if the corresponding fault happens to be here, the voltage collapses. So, from 0 value to consider increase from this one, and after you consider the capacitor it again decreases. So, at bus N the ratio becomes 1 theoretically. As the fault nears the considered relay, the measured voltage decreases, the calculated voltage increases and the ratio decreases. So, what we see that the ratio, that is the V measured upon V calculated becomes measured value is 0. So, that becomes increases like this and again decreases after the capacitor. This ratio is useful in determining the corresponding the position of you can say that the fault, whether it is beyond the capacitor or before the capacitor. So, when the ratio is less than the threshold, a threshold is selected suitably depending upon the reach of the line, the zone 1 distance, and otherwise you can say the algorithm blocks. If the threshold you can say that the threshold computed by this one in the real time by the relay, if the ratio is less than the threshold, zone 1 is allowed to operate. However, if it is beyond the threshold, the zone 1 is not allowed to operate. So, with that philosophy you can say that with the series compensation algorithm, the zone 1 reach is set based on the line impedance, and additional information needed on x c, that is whether the corresponding x c you can say is encountered in the fault loop or not, and that is by the consider the ratio, voltage ratio, and that voltage ratio decides zone 1 will be in operational or blocked. Now, let us consider example 400 kV line 365 km as we have seen earlier, 40% compensation. So, what we did here you can say that we created fault at different points along the line, 10%, 30%, 50%, 70%, 90%, point P just before the capacitor and just after the capacitor at bus N. So, we created fault and then you can say that we measured the voltages at here as seen by the relay through the simulations, and we calculated the voltage using this relation, and then you can say that we computed the ratio for you can say that all the points. So, these ratios you can say that are plotted here, along you can say that the corresponding calculated value of the voltage and also the measured value of the voltages. So, what you find you can say that the if you put you can say that a selective threshold value, then if the less than the threshold value, then zone 1 will be allowed to operate, otherwise zone 1 will not be allowed to operate. So, this is a voltage ratio based driven based you can say that zone 1 operation, and which can be also applied for transmission and protection in this kind of scenario. So, in overall we see that in the apparent impedance calculations, zero sequence compensation factor plays a role, and which is a function of x now the fault distance and difficult to calculate correctly. Both bus side and line side you can say that locations of the relay and the measurements, associated measurements have some advantage and also some demerits also. Distance projection faces serious difficulty during low current situations, when the corresponding MOB may operate and may not operate, that the consider that issue. In the fault happens to be the close to the considered series compensation, inversion voltage and current inversion may create problem, even to the apparent impedance calculations will be observed in the fourth quadrant also. Distance protection overreaches due to the series compensation, that is another you can say that. So, that again subsynchronous oscillations also during that few cycles also creates problem. We found that some solutions perspective, current control adaptive resetting and voltage ratio approach are the two methods we describe in this one as solutions to the series compensator line. So, in this perspective we see that series compensation has a great challenge to the distance relay operations, distance relay settings, distance relay performance. Thank you.